Okay. So, hello everyone. I'm Gitanjali Jaina. I'm a PMRFT from IIT Delhi. So, as I said before, in each live session, we'll go through the weekly content and I will solve some numerical problem which is related to the concept of the weekly content. So, in this week, we typically studied about the directional coupler and what are the principles of uh, wavelength division, multiplexing, and demultiplexer devices. So, sorry. So for this lab section, I will go through the some numerical problems and some conceptual problems that is related to directional coupler as well as the wavelength division multiplexer. So without any further delay, so let me start our first question, which is based on directional coupler. And before starting the session, before the starting the to started before starting solving the problems, so if you have any doubts in any of the steps during the calculation, feel free to stop me at that moment to clarify your doubts. As well as you can ask any conceptual problems that you can have regarding the concept that is related to the weekly content. So let me start the first question, which is based on the directional coupler. So the is so let me read the question once. Consider a directional coupler consisting of two non-identical waveguides such that its coupling length is 1.5 mm, and if the maximum power coupled from first waveguide to the second waveguide is 81%, obtain the value of its delta beta, which is the phase mismatch and the coupling coefficient. So, if you recall, directional couplers, they are typically the general schematic is they made up of two single waveguide, two identical or non-identical waveguides, which can couple with each other to enhance the to what I say to um, to make the interaction between the modes that is propagating in individual website. So this is the general definition of a directional coupler. And if you recall the power distribution for a non-identical waveguide. So let's say we have waveguide 1 and waveguide 2. So the distance between them is small so that the interaction can take place between these waveguides. And the power distribution, so let's say we are feeding P0 amount of power, and the power that couples to this waveguide 1 is P1Z at different length and P2Z for this waveguide. And the ratio, it can be calculated through coupled mode theory by making approximation to the waveguides, to the web modes that is propagating inside the fiber and the coupling coefficient. So if you recall P1Z by P0, it is given by 1 minus kappa square, gamma square, sine square, gamma z, and P2Z by P0 is kappa square, gamma square, sine square, gamma z. And by coupling length, we mean that whatever amount of power that is coupled to waveguide 1, it is transferred to waveguide 2. So that means here at this coupling length, no power will flow in waveguide 1. The maximum power, all the power will be coupled to waveguide 2. And so that means P2Z by P0, it will be maximum at this coupling length which is at Z equal to LC. And this the maximum value of sin square is 1. So that means P2Z by P0 is kappa square over gamma square. And this can only occur when we have sine gamma z, that is gamma z, which is the angle is pi by 2. So that means the coupling length for a non-identical fiber, you can write the coupling length is pi over 2 gamma. And if you recall, for identical waveguide, the gamma is simply replaced by kappa. Instead of gamma, we have kappa. So let's see what we have now. So in the question, it is already given the coupling length is 1.5. So that means we can write gamma is pi by 2 LC. So we can calculate it. This is to 1.5. So pi by 3 millimeter inverse. So this is the value of gamma we have. Let us see what we need to find out. We need to find out what is delta beta and what is the coupling coefficient. So for that, what we can do, we can use what is the information given, that is maximum power coupled from first waveguide to the second waveguide is 81%. That means this is the power coupled at the coupling length because it is the maximum power. So we have P2Z over P0 at Z equal to LC is 81%, 0.81. So this is equal to kappa square over gamma square. Gamma we already know. We calculated using the coupling length. So that means now we have kappa square is 0.81 gamma square. So kappa, which is the coupling coefficient, it is square root 0.81 means 0.9 and gamma. So just put the value of gamma, which is 0.9 pi by 3. So this will give 0.3 pi millimeter inverse. So now we calculated what is the second question, that is what is the coupling coefficient for this waveguide, which is 0.3 pi meter inverse. For delta beta, what we can do, so you already know gamma square, it is related to both kappa square and delta beta tilde square over 4. We know gamma here, we know kappa here. So we can easily calculate what is delta beta square, which is 4 times gamma square minus kappa square. So delta beta, this is simply 2 square root gamma square minus kappa square. So this is, let me put the values. Gamma square is pi by 3, right? So pi square by 9. And kappa square is 0.35, which is 0.09 pi square. This will give 2 pi square root 1 by 9 minus 9 by 100, and this will give 0.29 pi millimeter inverse. So delta beta, we got it is 0.29 millimeter inverse, and the value of coupling coefficient is 0.35. So this we can calculate it using this. Okay. Next question is, it is, let me next one. So the question may seem lengthy, but if you go through all the instruction that is given, then you can calculate it. So the question is, a directional coupler is made with two non-identical single-mode waveguides such that the difference of their propagation constant at wavelength lambda is given by this. So let me sequentially write what information that is given to us. So delta beta is given, which is beta minus beta 2, which is minus alpha lambda minus lambda 0. So you can take it as take it as this is delta beta. Okay. So because in class it has been noted as delta beta, so it's better to take that only. Okay. So delta beta is given. What else is given is the value of alpha is given, which is pi into 10 to the 5 millimeter square, and lambda 0 is given, which is 0.6 micrometer. The interaction length between the two waveguides is 1 mm. So that means, let's say it is single mode, this is also single mode. This length, where they are in close proximity with each other, this length L is given 1 mm. And interaction length of this two waveguide is 1 mm, which is also equal to coupling length of the coupler at lambda equal to lambda 0. So this is equal to LC at lambda equal to lambda 0. Assuming that the coupling coefficient doesn't depend on the wavelength, calculate the value of coupling coefficient in the powers at the output ports at lambda 0.61 micrometer for unit input power coupled in one of the input. So what it say? You feed P0 is 1 milliwatt or 1 watt, whatever unit you can take. So P0 is 1 watt is fed into this directional coupler. So the question asked about what is the coupling coefficient. It lambda is 0.61 microampere, micrometer, and what is the power at the output ports? That is what is P1 and what is P2 at lambda 0.61. Given this information to us. So, okay. So let us see what is the parameter that we can get from the given uh, information. It is given L 1 mm and it is correspond to the coupling length at lambda equal to lambda 0, which is lambda 0 is 0.6 micrometer. Sorry. So let us see. So if we recall, for a non-identical waveguide, LC, it is given by pi by 2 gamma. So that means we can easily get what is the value of gamma for our case. So gamma will be pi by 2 LC. So gamma depends on the wavelength, but in the question it is given kappa is independent of wavelength. So we can use same gamma for 0.61 microamperes. Sorry, micrometer. So this is pi by 2. LC is 1 mm. So pi by 2 into 10 to the 3 meter inverse. This is the value of gamma we get. If you calculate it, it will come around 1.57 into 10 to the 3 meter inverse. Now for the value of calculating the coupling coefficient. So if you recall, gamma square is kappa square plus delta beta square by 4. We know gamma, but we can calculate this value, then we can easily calculate what is the value of kappa now. So delta beta delta is already given, this expression. So that means that delta beta delta is, let me see, this is minus alpha lambda minus lambda zero. Alpha is given pi into 20 5, and lambda minus lambda zero, it is lambda is 0.61 micrometer and this is 0.6 micrometer. So while calculation, please remember whatever the unit uh, you want to take. So I have already calculated it is meter inverse. So let us calculate here also. Micrometer is 10 to the minus 6 and millimeter. So there is a millimeter inverse there. Millimeter square. This will give 10 to the 6. So that means this will cancel. What we have now is minus 5 10 to the 5, 0.01 meter inverse. This will give minus 5 millimeter inverse. Okay. So we calculated what is the value of delta beta or delta beta delta. Now we can easily calculate what is the coupling coefficient, which is kappa square. This will be gamma square minus delta beta tilde square by 4. Gamma square is, so let's take the square root. Gamma square. So gamma is pi by 2 and 20 by 3, right? This one. So this is pi by 2, 20 by 3 square. Delta beta tilde is pi square by 4. So this was in meter inverse. Okay. That means now here we have 25 feet. Right? Because here you see here is minus 5 into 10 to the 3 meter inverse. So if you put calculate the overall expression is 10 to the 3, this will be pi by 2 square minus pi by 4 square. So this will give pi by 2 . So you will get root 3 pi by 4 meter inverse. And there is 10 to the 3 also here. So you can write it as root 3 pi by 4 millimeter inverse. So this is the value of coupling coefficient now. So now we can easily calculate what is the power at the output end, because we know gamma, we know L. So we can calculate what is the power. 1 minute. So power at the output port, given P0 is 1. So P1 at Z equal to L is 1 minus kappa square gamma square sine square gamma z, and P2z, it will be kappa square gamma square sine square gamma z. What is the value of z? It is given the interaction length is 1 mm. So that means z is value is 1 mm, and gamma we have already calculated, it is pi by 2 millimeter. So that means P1z is 1 minus kappa square gamma square sine square pi by 2. Z is 1. So this is 1. 1 minus kappa square gamma square. What is kappa now? This one. Root 3 pi by 4. Root 3 pi by 4 square. Gamma is pi by 2. So just calculate it. You will get it is 1 by 4. So this is nothing but 0.25. So that means 25% of the input power it will couple to the waveguide. For waveguide 2 is P2Z. It is kappa square gamma square sine square gamma z. So this is kappa square over gamma square. So you can use also because so instead of calculating all this, what you can do P1z plus P2z, it is easy, right? So that means P2z will be P0 minus P1z. P0 is 1 and this is 0.25. This is 0.75. So 75% of the input power will be coupled to the second waveguide and 25% will be coupled to the first waveguide. It is coupling waveguide. So please be careful while calculating these powers because the power coupled it depends on what is the length, what is the interaction length of the two waveguide of the directional coupling. So it is coupling length 75% couples to P2Z and 25% remains in the waveguide 1. So let us move to our next problem. Please go through the question once. Okay, it is somewhat similar to what we have seen in question number 1, I think. Yes. So consider a directional coupler consisting of two non-identical waveguides such that its coupling length is 2 mm. If the maximum power coupled from the first waveguide to the second waveguide is 64%, then obtain the value of its uh, delta beta and coupling coefficient. So you can take it as delta beta tilde instead of delta beta. So NC is given, then we can calculate for non-identical waveguide. We can calculate what is the value of gamma because gamma it is pi by 2 LC. LC is 2 mm, so this is pi by 4 mm inverse. So now we have what is the So maximum power coupled from first waveguide to the second waveguide is 64 percentage. So that means we have now is P2 Z P0 max, which is kappa square over gamma square. And this is equal to 0.64. Gamma we know, so that means we can calculate what is the value of kappa. Kappa will be gamma square root 0.64, which is 0.8 gamma. So gamma is pi by 4. So this will give, we have 0.25 millimeter units. So this is the value of coupling coefficient of these two waveguides. For delta beta, we can cross calculate it from the expression of gamma. Gamma is pi by 4. So this is kappa square plus delta beta tilde square by 4 is pi by 4 square. So delta beta square by 4 pi square by 16 minus pi square by 25. This will give 9 pi square by 100. So that means we have now delta beta square is 9 pi square by 25. So delta beta is 3 pi by 10, which is 0.3 pi mm. Okay. So while doing all this, please be careful whether the waveguide is identical or not. And what is the expression for maximum value of power in second waveguide and maximum value of power in first waveguide. Okay, so let us move to the next problem. So do you have any question till now? I think you may not have because the questions are easy. Okay. Okay. So let us move to our next problem. Next problem is based on identical waveguides. So consider a directional coupler consisting of two identical waveguides such that its coupling length is 2 mm. Obtain the minimum value of the interaction length for realizing a 3 dB coupler and 80-20 splitting at the two output poles. Okay. So first we need to calculate what is the value of interaction length for 3 dB coupling and what is the value of interaction length for 80-20 splitting. If you recall in identical waveguide, the delta beta tilde, it is 0 because beta 1 is equal to beta 2 and the interaction terms, these are also equal because they are identical. So that is why we have this condition. In such case, the gamma square, it is equal to kappa square. So we can simply replace gamma by kappa. And the expression for powers is P1Z by P0. It is 1 minus kappa square gamma square sine square gamma z. If you put k now instead of gamma, we have 1 minus sine square kappa z, which is cos square kappa z. Similarly, P2Z, it is kappa square gamma square sine square gamma z. That means this is equal to sine square kappa z. So let us see what is the interaction length for 3 dB coupling. So 3 dB coupler means, what is the meaning of 3 dB coupler? So this means 3 dB coupler means we have 50% power in the input port and 50% power in the cross port. So there is a 50-50 power splitting. Yes, 50-50 power splitting. So that means you can get it from using the formula alpha is 10 log 10 P in P out. So this formula you are familiar with, I think. So P in by P out. So if it is P out is half when P input is 1. So that means this is 10 log 10 2. And if you calculate it, this will come around 3 dB. So that is why we call it as a 3 dB coupling. Okay. So now we have P1Z over P0. It is, and P2Z over P0 is half. What else is given to us? The coupling length is 2 mm. Okay, so coupling length is 2 mm means LC is 2 mm. So this is pi by 2 kappa, right? This is 2 mm. So that means you can get kappa from here, which is pi by 4 millimeter. So we know kappa now, and power is already given to us. So that means we can calculate what is the length now. So P1Z by P0, it is half. So that means cos square kappa Z, it is half. So cos kappa Z, it is 1 by root 2, which means this is cos pi by 4. So that means now we have kappa Z is pi by 4. So Z is pi by 4, which is kappa, we got it around pi by 4, right? This is pi by 4. This will give 1 millimeter. So that means at this wavelength, at this interaction length, we will have 50-50 power in both the input port and the output waveform. Now let us see the second one, which is 80-20 scale. Here you can see, depending on the interaction length, we are getting different amount of power at the output port. So that means the interaction length, it depends on what is the length of the interaction region. Okay. So 80/20 means P1Z by P0 is 80 percentage, which is 0.8, and P2Z by P0 is 0.2. This is cos square kappa Z, which is 0.8. So cos kappa Z, this will come around 0.89443, and kappa Z is 0.46365. So if you take the cos inverse, you will get it. So Z, it is 0.4636545. So that means we have now is this is 0.59 millimeter or 0.6 millimeter. So for 80-20, we need to have the interaction length as 0.59 millimeter. In 1 millimeter, we have 50-50, and in when you when you decrease the interaction length, now the splitting is getting increased to 80-20. Okay. Let us move to our next problem. So next problem is a bit conceptual one. Please go through the question once. And let me know what is your answer for this. So to summarize, there are two directional coupler. Each directional coupler have identical waveguide, which are single moded, you can take it. And the first directional coupler has N1 refractive index in the core, and the second directional coupler has N2 refractive index in the core. The geometrical dimension are equal. Other than that, only the refractive index of the core is changing. And it is also given N1 is greater than N2. Then which coupler has larger coupling length and why? So to give you it, just relate the coupling length with the refractive index, how they are related. Then you can easily guess it which one of the directional coupler has last coupling length. It is related to gamma. Yes, it is also related. If you take non-identical, then it is related to gamma. And how gamma is related to refractive index? Okay, so let me tell you the answer. So if you take identical or non-identical, both will give same answer because the only difference is delta beta. Delta beta will be there in the gamma, or it is zero uh, in the identical waveguide. So if I take identical waveguide, then what is LC? So LC is pi by 2 kappa, right? And kappa is nothing but the coupling coefficient. So it depends on the coupling coefficient of the two waveguides. Now let us see what we have. So we have two directional coupler now. Here it is N1, here it is N2. And it is given N1 is greater than N2. N1 will have a smaller LC. Why? So let me see what is the concept, what is the concept that you have used for finding N1 will have smaller LC. So the answer is just opposite to what you say. It's like N1 will have larger LC than N2. Concept is intuition. The laser refractive index confine the pulse more. Yes, laser refractive index means they will confine the pulse more. The pulse will be more confined in the core. So it takes longer distance to move to the other. Yes. So you got it, I think. So refractive index more means it will be more confined to the core layer than in the cladding layer. So that means the interaction, that is the kappa. These are related to kappa, right? So kappa in such case will be small, but here these are linking to the cladding layer. So kappa here will increase for low refractive index. So that means kappa 2 is greater than kappa 1. So that is why LC1 it is greater than LC2 because LC is inversely proportional to kappa. So you got it right. Okay. So let us move to our next problem then. Please go through the question notes. So so if you look at it, these are two directional coupler. Okay, so this is so the question says a directional coupler with two identical waveguides is designed to have a coupling length of 2 mm. What is the permissible variation in the fabrication length of the coupler? So what is L here? Length so that in the cross state, if unit power is incident on waveguide 1, then the power emerging from the same waveguide is less than minus 20 dB. So it is saying what is the permissible variation in L, that is L plus or minus delta L, so that we can have the power in the same port, that is P1. P1 is less than minus 20 dB. So what you can do here? So first we need to change the power from minus 20. So we have to convert the linear power. Mm, okay. So 20 dB is given. So you need to first convert power from 20 dB to a linear unit. Okay. So linear means, so if you recall alpha, it is given by 10 log 10 P1 by P0. P out by P in, right? P1 by P0. And alpha, it is already given, which is minus 20 dB. So minus 20 dB, this is 10 log 10 P1 by P0. So you can easily calculate what is P1 by P0. So P1 by P0 is 10 to the power minus 2, which is 0.0. So that means we need to have the power in the first port should be less than 1 percentage, right? Which is equivalent to minus 20 dB. So now let us see what is the expression for identical waveguide. So we'll start from there. So for identical waveguide, so if you recall, we have P1Z, it is P0, cos square kappa Z, and P2Z, it is P0, sin square kappa Z. So P0 is already given. Unit power is incident on waveguide 1. So P0 is 1. So that means we have P1Z equal to cos square kappa Z, and P2Z, it is sin square kappa Z. And what is the coupling length for the identical waveguide? So coupling length for identical waveguide is LC, right? LC is nothing but pi by 2 kappa. So we can express the powers in terms of LC. So P1 is cos square. Kappa is pi by 2 LC. So pi by 2 LC. Let us say Z is L and P2Z is. So we are just expressing the powers in terms of the coupling length. Pi by 2 LC L. So that means when L equal to LC, that is where if the interaction length is LC, so power in the first port, it will be 0. But it is asking to calculate what is the fabrication error that the waveguide can tolerate so that the power in the first port is less than 0.01. So let us say the length is LC plus or minus delta. So we will calculate the length in terms of LC because LC will remain constant for a given length of the fiber for a given parameter of the fiber, right? So if the kappa remains same, the LC will remain constant. So that is why we have taken this constant to express the fabrication error. Okay. So this means the power exit that will exit from the first waveguide. This would be P1 LC plus or minus delta L, which is cos square pi by 2 LC. L is LC plus or minus delta L, and this is cos square of pi by 2 plus or minus pi delta L by 2 LC, and cos square pi by 2 plus or minus this, if you use the cos A cos B formula, cos A plus B formula, so this will give sine square pi by 2 delta L by LC. So this is the final expression for power in terms of the fabrication error. And it is given P1, it should be less than 0.01. So that means sine square pi delta L by 2LC should be less than 0.01. So if you take sine square the other side, you will get pi delta L by 2LC. It should be less than 0.1. So it will come around 0.1. So that means delta L now is 0.2 LC by pi. And LC, it is already given in the question. I say, yes, it is given a directional coupler with two identical waveguide is designed to have a coupling length of 2 mm. So that means this is LC is 2 mm. You just need to put it here 0.2 by pi. So this will give 0.13 mm. Okay. So this is the fabrication error. That is, if the length is plus, it is greater than 0. So if it is within the range 0.26 of to the left of L and to the right of L, then the power will still remain less than 1%. Okay. So this is how you can calculate what is the fabrication error. 2 mm. Oh, okay, sorry. So is this clear, this problem? Okay. So let us move to our next problem then. It is given, shown below is P2Z in a directional coupler when unit power is incident at Z equal to 0 in waveguide 1. The maximum coupled power is 0.81 and the coupling length is 5 mm. Obtain the value of kappa, delta beta of the directional coupler. What is the distance from the input end where the power is equally divided between the two waveguides? Okay. So we are given P2Z by P0, the maximum value is 0.8. You can see here also the maximum is 0.8, and here also if you see this is at 5 mm. So that means the coupling length is 5 mm. So we have P2 over P0 max, it is 0.81. First, let us calculate what is the value of gamma now. So coupling length is 5 mm from the figure, or okay. So it is gamma LC, it is pi by 2. So that means gamma now is pi by 2 LC. So pi by 10 millimeter in. So this will become around 100 pi meter in. And this P2 by P0 max, this we have already seen. This is kappa square over gamma square, which is 0.8. So that means kappa is now square root 0.81 means 0.9 gamma. So gamma is 100 pi meter inverse. So this will be 90 pi meter inverse. So we got the value of kappa now. And beta, delta beta is easy to calculate it from gamma. Gamma square is kappa square delta beta square by 4, which is equal to 100 pi square. And gamma is 100 pi square and kappa is 90 pi square plus delta beta square by 4. So just rearrange the terms. Delta beta square, which is 4 times 100 pi square minus 90 pi square. This will give 2 pi square root 100 square minus 90 square. So which will be 87.85. This is the value of delta beta tilde. This is the first part of the question. In the second part, we need to calculate what is the distance from the input end where the power is equally distributed between the two waveguides. So this is like what is the interaction length for 3 dB coupler. So we have P2 L. Let's say at a L distance it is half kappa square gamma square sine square gamma L, which is 0.5. So this is sine square gamma L. The value for gamma and kappa we already know. So just put it in the equation. So what is the value of kappa? Is 90 pi. So this will come around if you take the square root sine gamma L, it is 10 by 9 square root 0.5. So L will be 1 by gamma sine inverse 10 by 9 root over of 0.5. So this is 100 pi sine inverse. Okay. So this will come around 2.87 millimeter. So at this length, the power will be 50-50. Okay. So we got the value of A and B. Now what we, okay. So this is clear, right? This is easy also. Okay, we'll move to the next problem. Please go through the question once. So the question says, consider a directional coupler with the coupling coefficient kappa as 0.282 millimeter inverse. And it is given so kappa is 0.282 millimeter inverse. If we require maximum fractional power in coupled port greater than 0.04, then what is the maximum difference delta beta at the wavelength 1530 nanometer is? There are four options that is given to you also. So coupled port means the power in the second port. So if you recall P2Z by P0 max, it is alpha square, gamma square, sine square, gamma z max, which is alpha square over gamma square. And it is given the maximum fractional power in coupled port should be greater than 4%. So that means P2 over P0, it is greater than 0.04. That means kappa square over gamma square is greater than 0.04. So kappa square is, so let us rearrange. Gamma square is less than kappa square over 0.04. Kappa is already given, so you can put it is 0.282 millimeter inwards, 0.04. So this will come around 1.9881. So that means gamma is, so let us put gamma square first. So kappa square plus delta beta tilde square by 4 should be less than 1.9881. So just rearrange the equation. This is 1.9881 minus kappa square. Kappa square is, this is 0.282 square. So the overall, this will come around 1.908576. Okay. So now we have what the question asks. Delta beta is less than 2 square root 1.908576, which is 2.76 millimeter, which will come around. So if the options are okay, so this is closer to 2.8. So that means the answer will be 2.8. So the maximum difference should be, maximum difference is 2.8. Okay, so let us move to our next problem. So the question says a wavelength division multiplexer WDM has a coupling coefficient K lambda 1 is 0.7 millimeter inverse, K lambda 2 is 0.35 millimeter inverse. If a beam containing wavelengths lambda 1 and lambda 2 is fed into the input port of fiber 1, then what is the minimum operating length required to separate the beam? So we have identical waveguide and we inject lambda 1 and lambda 2 here, and we want to separate it out in output. And it is also given what is the value of coupling coefficient at different wavelength. If you recall, we have so always start from the concept that you know. So P1Z. Sometimes just writing the formula, it may be you will you may write wrong formula. So better to start from what is the formula, what is the concept you know. So P1Z over P0 is cos square kappa Z, and P2Z by P0 it is sine square kappa Z. So for WDM of length L, so let us say the length is L here, interaction length. So P1Z by P0, it is cos square kappa L, and P2Z by P0 is sine square kappa L. And if you recall, if you want to separate out the lambda 1 here, so for P1 put, we have cos square kappa L. So that means KL should be some multiple of pi so that it can come out through this port. And for lambda 1, if you put the formula for P2, which is sine square kappa L, so when kappa L is m pi, this P2 will be 0. So that means for lambda 1, if I take kappa lambda 1 L is m pi, then we have P1Z is P0 and P2Z is 0. Similarly for lambda 2. So for this branch, what is the formula for power? It is in terms of sine square kappa L. So that means if I take kappa L to L as m minus half pi, that is some multiple of pi by 2. So odd multiple of pi by 2. So this will give, this is 1, here it will be 1 because this is sine square pi by 2. But here it is cos square pi by 2, so it will vanish. So P1Z now here is 0 and P2Z it will be P0. So for this condition, we can separate out the lambda 1 and lambda 2. So length, we can calculate it if you take the difference. So this will be K lambda 1 L minus K lambda 2 L. It should be pi by 2. So the minimum length is pi by 2. Minimum difference. This is K lambda 1 minus K lambda 2. This is pi by 2. So we have L as pi by 2 K lambda 1 minus K lambda 2. And K lambda 1 and lambda 2 is given. So this is K lambda 1 is 0.7 millimeter inverse and K lambda 2 is 0.35 millimeter inverse. So this is pi by 2.7 minus 0.35, which will come around 4.48. At this interaction length, we will have lambda 1 coming out through port 1 and lambda 2 coming out through port. So we can separate out the two wavelengths. Okay. So let us move to our next problem. Please go through the question once. So the question says, consider a directional coupler with kappa as 0.2 mm inverse. If the maximum coupling power to cross port should be less than 1%, then what should be the minimum difference between the effective refractive indices of the propagating modes in the two waveguides at lambda 0, 1.3 micrometer? So let me write down what is given to us. So we are given kappa is 0.2 millimeter inverse and maximum coupling power to the cross port, that means to the port 2, is P2 over P0 max is less than 1%. Then what should be the minimum? So what is delta N effective for the propagating mode in the two waveguide at lambda 0, 1.3 micrometer? So how you can approach this question? So directional coupler, there are two waveguides. Let's say the propagating mode in this waveguide is refractive index and effective. So whichever mode is propagating, they have certain value of effective refractive index. So for this one, this is 1, and for this one, an effective 2. So these two have two different refractive index. Then the question is asking about what is the minimum difference between this refractive index for the propagating mode in the wavelength lambda 0 is 1.3 micrometer, such that the P2 by P max, P2 by P0 is less than 0.01. So how you can relate delta N now? If you recall, so P2 over P0, so delta N effective, you can relate it to delta beta tilde, right? So this is the difference between the propagation constant. So we can relate it to delta beta tilde. So first you need to calculate what is the value of delta beta tilde. From that, you can use the formula and calculate what is the minimum difference between the delta and delta beta tilde. You can calculate it because P2 by P0 max, the maximum value is, this is kappa square over gamma square. It should be less than 0.01. So this is kappa square plus delta beta square by 4 should be less than 0.01. Kappa square, it is given 0.2 mm in. So this will be 0.2 square, 0.2 square, delta tilde square by 4 should be less than 0.01. 0.04, 0.04 plus delta beta square by 4. So if I rearrange the LHS and RHS, we have 0.04 plus delta beta tilde square by 4 should be less than 4 by 1. 4 less than or greater than? Should be greater than, right? Yes. So now we have delta beta tilde square by 4 is 4 minus 0.04. And if you calculate what is the value of delta beta, this will come 4 millimeter units. So we know what is the value of delta beta now, delta beta. Now this propagation constant. So if you recall K, you can write it as K0 and effective, right? K is nothing but beta, beta 0 and effective. So delta beta will be beta 0, delta and effective, right? This you already know. So I'm just using the general formulation that we know. So this is beta 0, delta and effective greater than 4. Beta 0 is 4 pi over lambda 0, delta and effective. So delta and effective will come around 4. Lambda 0, it is given in the, 1.3 micrometer. 1.3 into 10 to the minus 6. Within that, what we have, this is 3.14 and 10 to the minus 3 for this millimeter unit. So this will come around 8 into 10 to the minus 4. So that means the minimum difference between the effective indices, it should be in the order of, it is 8 into 10 to the minus 4. Okay. So is this clear? Yes, we will get 8 into 10 to the minus 4 for this. So do you have any query till now? Otherwise, we'll move to our next problem. The next problem is based on the WDM coupler, but it's a slightly different one. So you need to use different concept to get the answer. So please go through the question once. The questions are visible, right? Or do I need to write it in bigger font? Okay, so go through the question once, then I will solve the problem. So let me read out first. It says consider a directional coupler made with two single mode waveguides whose modal effective indices at wavelength lambda are given by n effective 1 is 1.6 minus a lambda, and n effective 2 it is 1.55 minus p lambda. So for a particular wavelength of lambda, n effective for this directional coupler are given. A and B, these are constant, such that the two effective indices are equal at lambda equal to 1 micrometer. Let's say lambda equal to 1 micrometer is lambda 1. Further, the interaction length is 1 mm, which is also equal to 1 coupling length of the coupler at lambda 1. Assuming that the coupling coefficient is independent of lambda, obtain the nearest wavelength on both sides of lambda 1, which can be multiplexed or demultiplexed along with lambda 1 by the coupler. So we have these refractive indices, and it is also given that these are equal. So n effective 1 is equal to n effective 2 at lambda equal to lambda 1, which is 1 micrometer. And the interaction length is, which is L is 1 mm, and this is equal to LC at lambda equal to lambda 1, which is 1 micrometer. So what is the nearest? So we have this coupler lambda 1. So we need to find out what is plus or minus delta lambda, which can be multiplexed and demultiplexed through this system. When we have n effective as this and n effective is 1.55 being minus b lambda. So let us first calculate what is the value of A and B. So let us first define delta n, which is n effective 1 minus n effective 2. So this will be 1.6 minus A lambda minus 1.55 minus B lambda, which is 0.05 minus A minus B lambda. So for lambda equal to lambda 1, which is 1 micrometer, these n effective are equal. It is already given. So this will give delta n is 0. So that means 0.05 minus A minus B, lambda is 1 micrometer. This is 0. So A minus B is 0.05. So this is the value for the constants. The difference between the constants. So now we can rewrite delta n as 0.05 minus 0.05 lambda, which is 0.05 1 minus lambda. Okay, so now we have rewritten delta n in terms of lambda, and we have omitted what is the value of A minus B. The second information that is given is interaction length. This is one relation. One is next is L is 1 mm, and this is it is given it is equal to LC at lambda equal to 1 micrometer. So whatever information is given, try to use that to get some values that can be useful, some values of the parameter that can be useful to you. So LC is given. So this you can write it as pi by 2 kappa array, which is 1 mm. So we can get the value of kappa now, which is pi by 2 millimeter inverse. So this is the maximum information that we can get from the instruction. Okay. Now let us see what the question is asking about. So we need to find out what is lambda 1 plus or minus delta lambda. So if you recall, let us see the graph first. So the graph for multiplexing and demultiplexing. So if you recall, it's already there in the lecture. This is the power versus Z. So one graph. So if I say there are two wavelengths that need to be multiplexed or demultiplexed, let us say lambda 1 and lambda 2, and let us take lambda 1 is greater than lambda 2. So for this case, what we have, the variation of power this is for lambda. For lambda 2, what we have is this. This is for lambda 2. So graphs are not perfect, but okay. So it's like a, not like a step function, but like this. So in this graph, you can see the coupling length for pretty different color. So this is the, for lambda 1, what is the coupling length? These are the coupling length. Here we have LC lambda 1. Then again, here also, this is LC lambda 1. And here, LC lambda 1. And for lambda 2, the coupling length is from here to here. This is for lambda 2. And the second coupling length is here, LC lambda 2. Right? So if you look at the reason, this reason, so if you look at this reason, here you can clearly see, for this reason we have maximum power for lambda 2 in one port, and in that port the power of other wavelength is 0. So that means this is the length at which we are getting the demultiplexing behavior. So to separate out these two wavelengths, what we need to have is that, uh, so to conclude, to separate lambda 1 and lambda 2, we need the interaction length. It should be, in terms of lambda 1, it should be 3 times LC lambda 1, or it should be 2 LC lambda 2. So is this clear? Because only when in terms of lambda 2, it is 2 LC lambda 2, right? So at this reason, we will get a demultiplexing behavior. So lambda 1 will go through one port and lambda 2 will go through one port. So we will use this condition to get what is the nearest wavelength that can be multiplex or demultiplex along with lambda 1. Okay. So for demultiplexing, we need to have L should be 2 LC lambda. So now L is already given. It is pi by 2 kappa, and 2 LC for lambda 2, you can write it as pi over pi by 2 over gamma, which is kappa square plus delta beta tilde square by 4. So now it is. So first you need to derive this condition. If this is clear, then other things are easy to calculate. So if I rearrange, this is kappa square delta beta square by 4. 2 will cancel. So we'll get 4k square here, and delta beta square by 4. This is 3k square, and this will be root 3 plus or minus root 3 up. So delta beta tilde will be plus or minus 2 root 3 kappa. So to find out what is the lambda value, what we can do, we know the expression of delta n in terms of lambda. So if you can find delta n also, so in the LHS side, if we find delta n in terms of other expression of lambda, then we can equate it and find out what is the value of lambda. So for that, what we can do, we can use this value of delta beta tilde. So this this you can write it as beta 0 delta n effective, which is plus or minus 2 root 3k. Beta 0 is 2 pi over lambda 0 delta n effective, which is 2 root 3k. So delta n effective, it is plus or minus 2 root 3k. If I take lambda 0 as lambda, so this is 2 pi. That means this is plus or minus root 3k lambda by pi. So this we also got. So using delta beta, we get another expression for delta n, which is also in terms of lambda. Okay, and the value for k, we can simplify it further. This is pi by 2, the value for k, pi lambda. So this will be plus or minus root 3 lambda by 2. And there is a millimeter here, so we can take it 10 to minus 3. Okay. So now let us solve it. So this is 0.05, 1 minus lambda, and this is plus or minus root 3 lambda by 2 into 10 to the 3. This is 5 by 100. This will cancel. So we have plus or minus root 3 lambda into 10 to the minus 2, which will be 1 minus lambda. So when you rearrange the LHS and RHS, we have lambda 1 plus or minus root 3 10 to the minus 2 should be 1. So that means lambda now is 1 by 1 plus or minus root 3 10 to the minus 2. So from here we will get two values of lambda. The plus value will give 0.983 micrometer and the minus value will give 1.0176 micrometer. So this is the values of the nearest value of lambda that can be multiplexed or demultiplexed with lambda 0, which is 1 micrometer. So this question was a bit long, but if you know the concept, so it was a bit conceptual. So if you know how you can multiplex and demultiplex using two wavelength and use the formulation for delta m, then you can calculate what is the nearest wavelength for demultiplexer. Okay. So is this clear? We'll move to our next problem. Okay. The next question is a bit conceptual one. So I would suggest please go through the options, whatever we have, and let me know the answer for this question. Okay. It is given, consider the following statement and list out the true options among these for a directional coupler. The first option is the periodic exchange of power between the two waveguides of the directional coupler is due to the evanescent coupling of energy of the individual propagating mode. Second option is incomplete transfer of power occurs when two waveguides are identical to each other. Third option is the power splitting ratio is independent of wavelength. And fourth option is the coupling between the waveguides of directional coupler becomes smaller as the phase mismatch of the propagating mode increases. So let me know which of the option you consider it as a true. Which of these four option is true and which are wrong? A is true. Okay. So only A is true. Any other option that you can think of? This is right. Okay. If I'm not able to find out, then let me. So A is true because in directional coupler, Whenever the total internal reflection occur between these two waveguides, so if you recall, if these are, let's say these are single mode waveguide, and so there are evanescent tail in the cladding region. And these evanescent tail interact with each other and which will give periodic exchange of power between these two waveguides. B, I think, is false. Yes, it is true. So B is false because complete transfer of energy will take place. Okay. What about C? Yes, power splitting ratio is independent of wavelength because if you see this one, the WDM part, for different wavelength at the same interaction length, the power splitting is different. So power splitting does depend on the wavelength. Interaction length is also depends on wavelength. What is the fourth option? WDM is not possible. Yes, sir, you are correct. Okay, so D option is also true. Okay, so D option says the coupling between the waveguides of directional coupler becomes smaller as the phase mismatch of the propagating mode increases. So we'll see in details in the next question how this is related to the how this option is true. So to give a conceptual hint, so coupling it is related to the efficiency of power transfer, right? So if the phase mismatch, if it is increases, so that means the gamma value will increase, right? And eta max, if you recall, this is kappa squared over gamma squared. Um, so if gamma increases, that means the power exchange to the port 2, it will decrease. So that means this is correct. The coupling between the two waveguides of directional coupler becomes smaller as the phase mismatch of the propagating mode increases. So we'll see in detail in the next question how this is true. Okay. For the for this question, what we have, so if I add few more, this question also asks about how the coupling length will be affected, how this will be affected, and how the coupling efficiency will be affected. If you see the options, so the question says draw the power coupling efficiency for the following cases. For the first one, delta beta is 4K. Second one, it is root over of 12K. Third one, it is 2K. And delta, in the fourth option, it is 0.4K. So it is gradually decreasing from 4K to 0.4K. Now let us see how the power exchange, the periodic power exchange will be get affected by this following option. So we have when delta beta tilde it is non-zero. That means we have non-identical waveguide. And for non-identical waveguide, we have P2Z over P0 is theta. It is kappa square, gamma square, sine square, gamma Z. This you can write it as kappa square plus delta beta delta square by 4 sine square. So I'm just rewriting it so that we can express the formula in terms of the given parameter. And P1 Z over P0 is, let us say this is zeta. This is 1 minus r squared or into Z. And the coupling length is LC, which is LC prime, let's say it is 2 gamma or pi by 2 square root upper square plus delta beta square by 4. Let us see the first case. The first one we have delta beta tilde, which is 4k. So for this case, if you find out what is the coupling length, which is LC prime, this is pi by 2 gamma. So do you have any query? Okay. So let us calculate what is the coupling length first. So delta beta tilde is 4k. So this, if you put it, this 2 k square, this will be 4k square. So this will come around. Okay. So pi by 2k root 5. And pi by 2k is the coupling length for the identical waveguide. So this is LC by root over of 5. And what is the power exchange? Eta max. It is kappa square over gamma square, right? So kappa square is kappa square plus gamma square is delta beta tilde by 4, which is 4k square, and this is 1 by 5, which is 20%, right? So this means only 20%, the maximum 20% is of the input power will be coupled to the out to the port 2. Other 80% will remain in port 1. So the graph will be like this. So if I take for port, this is for port 2 only. So this is Z, this is eta or theta. 0.2 will remain in port R2 and it will be like this. So this is 0, sorry, this is 1 and this is 0.8. So this is incomplete exchange of power. Just from the amplitude of P2 by P0. So larger the delta beta tilde, the smaller will be the power transferred to waveguide to along Z. So LC becomes longer. Mm. Okay, here I think you are talking about delta beta when it increases, then the eta max will now increase. Let me get to a question just from the amplitude of P2 P0. The larger the delta beta delta, smaller will be the power transferred in 1 minute. I think you are talking about this. Mm. So when um, delta beta will increase, sine square will increase, beta will increase. That is the coupling will beta max will increase. Okay. Mm. Okay, so there is a gamma square here also. Okay. So it's like, if you take the maximum, this is kappa square over gamma square. So when delta beta increase, this will increase, eta will decrease. So the coupling length will increase. Yes, you are correct. Mm. Okay. So we'll see numerical also. Numerically, we can see here. This will become around LC by root over of 5. And for the second case, that is B, which is delta beta, it is root over of 12. And if you find out what is the LC prime now, this is pi over 2 root over of k square plus 12 k square by 4. So this will come around pi by 4k or LC by 2. Hmm. I think coupling length, it is inversely related to gamma rate. If gamma will increase, LC will now increase, LC will decrease. So here if you say for delta beta tilde 4k, we got LCS LC by root over of 5. But for um, delta beta tilde, it is root over of 12k. LC prime is LC by 2. So here you can see the LC is now increasing, right? Here 2, it is root over of 5. So when you decrease delta beta, the coupling length, it decreases. No, when you increase, so when you decrease delta beta, the coupling length increases. It's inversely proportional. But we haven't. So in this problem, it was asking about what is the efficiency of coupling. It's not asking about what is the coupling length. It's like whether eta maximum is higher. So it was basically asking about what is how the eta max So coupling is basically decided by eta max, right? How much amount of power is coupled to port 2. So that is why we have looked in eta max for this. But LC, it is inversely proportional to beta, delta beta. So when it will decrease, it will increase. Okay. So if you plot the graph now, so the maximum power, uh, okay. So maximum power, so just first find out what is the maximum coupling power to port 2 for this case. So this is kappa square over gamma square. So this will come around kappa square plus delta beta square by 4, which is 3k square. So you can see eta maximum is increasing when you are decreasing delta beta. So when you are decreasing the phase mismatch, the eta max is increasing. 20% to it is coming around 25 now. Okay. So now we'll have eta, zeta, and this is z. So this will be 0.25 now. This is 1, this is 0.75, and this is 0.2. Now for the third option, we have in C part, it is now decreased further to 2 kappa. Delta beta will decrease. So LC prime will be pi by 2 kappa square, and this will also become kappa square. So this is pi by 2 root 2k, which is LC by root 2. So the LC, it is now increased further. So eta max will now increase kappa square, gamma square. So kappa square or so this is half, so 0.5. So the graph will now, if I draw it here, this will come here. So they will touch because 0.5 and here is also 0.5. Okay. And for the third case, we have delta beta delta is 0.4k. So that means LC will now increase further pi by 2 kappa square plus 0.4k square by. So this will come around pi by 2k square root 1.04. So LC by square root 1.04, which is approximately to 1. So eta max is now kappa square over gamma square, which will come around 0.96 if you put the value of kappa and delta beta. In this case, we'll see that when you decrease the phase mismatch further, the coupling efficiency increases. Now 96% of the power can be coupled to port 2, and the remaining 4% will remain in the port 1. So for port 1, so this will not touch the horizontal axis because 4% will remain in the port 1. So it won't become 0 now. Okay. So this is 1, this is 0.96, and this value is 4% is 0.04. So this is eta, this is zeta. And if you now compare the LCs, so we have calculated LC for all the cases. You can see the coupling length will increase. The coupling length increases when you decrease the delta beta. And the coupling efficiency will also increase from 20 to 96% when you decrease the delta beta. Okay. So this is all for today's tutorial session. So do you have any doubt till now? Let me clarify the doubt or we'll end the live session. Okay. 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 So let us meet on next Monday, same time from 6 to 4. Thank you for joining the live section. I hope whatever I have solved it is useful to you for solving the assignment problems. So we'll meet on next Saturday. Thank you everyone. Bye.